Hello everyone. In today's lecture, we're gonna talk about a new topic. In last few videos, we talk about several regressions. Uh, but by doing the either solve from the gradient descent algorithm or stochastic gradient algorithms by minimizing the cost function. But have you ever wondering why does that even make sense? In today's lecture, I just give you a little bit of justification for regressions. So that's the first topic. Statistical justification for regression. So far we have talked about regressions as a way to fit curves to points. Recall that actually at the beginning of the semester we talk about how can one using the machine learning techniques learning. There are a few parts you need to think about it. First is application. So what do you plan to use? Do you plan to design a new software to classify the spam emails, or do you plan to predict some temperatures? So far we talk about classification problems and regression problem separately. And once you identify your application problem, you start to think about the model you're trying to use. For example, for the classification method, we use the spectrum algorithm, support vector machine, logistic regression. And for the regression problem, we also have several models like a least square regression model, multinomial regression model, and weighted logistic regression, ridge regression, which we'll be talking next. And once you identify the model you're trying to use, and then you actually convert your problem to fit the data based on the data you have at hand. You convert your problem to be optimization problem. You want to minimize some cost, or you want to maximize some likelihood functions. And then we can identify some optimization algorithm. Okay. So in today's lecture, I want you guys to start to think about the second step, the modeling part. I describe some models and how they lead to these optimizations. Why do we optimize, for example, least square estimations for regression, linear regression? Why do we use minimize the logistic loss for the logistic regression? Actually, they are not just coming randomly with picking that loss. There is a motivation behind. So that's what I want to talk about next. And then I will also talk about there's an important concept called the Bayes variance decomposition. If you took my data science computing class, you already had some taste of the variance Bayes decomposition. Problem. Okay. Okay. So let's start. Give more details for each of the topic. So first, let's talk about so actually, when we apply the machine learning models for in our real applications, machine learning in application. Okay, we always have some data sets, so we have some sample points. From some unknown probabilities. For example, we always assume xi from the distribution follow some distribution. You can think in support vector machine, for example, we assume this is normal, for example, normal distribution with some mu and sigma square, right? And that's the input x. Where's the output y is? Y values are sum. Usually the y is, so for any x given x, yi is given by some function of the xi plus some epsilon I. Okay. This gx is a ground truth function. You can think this g is some ground truth function. And this is non-random. So this g not random. Okay. And this epsilon, this is error term, is from some measurement noise. So this is we assume this is follow some distribution noise epsilon from some distribution where this distribution commonly assumed has mean 0. Follow some distribution with mean 0. Okay, so in reality, we want to find some machine learning algorithms to figure out what's the ground truth function. So although we do not know this g is not random. It represents a consistent relationship between x and y. And we want to estimate based on some machine learning algorithm. We also add some random variable epsilon, which represents measurement errors and all other resources of statistic error when we measure the real-world problem. Note that the noise is independent of x because when we have the xi, the sample points, and then we try to observe y. So this is common to assume that epsilon I and xi are independent. So that's a quite a reasonable assumption. Often it does not so the bottom line is here x is some random variable, follows the distribution d, and y is also a random variable, but the random variable is generated by some function, the g xi plus some measurement error epsilon I. Okay, so and xi and epsilon I are independent. So the goal of the regression is to find some function f. For example, we can use some linear regression, polynomial regression, logistic regression, those f, to estimate this g. But now we know if we follow this setup, y and x are both random variables. Although x and epsilon are independent, but y is a function of both x and epsilon. So y and x actually is a let's use another notation. Usually f denotes some, let's use h function. Okay, so approach is to use in statistics we call it the conditional expectation. Conditional expectation is the conditional x equals to x. Find the expectation of y. So for example, in the linear regression, if you have the bunch of the dots here, and for each given x, we have the whole distribution for y. Right? We have given each x, we have a lot of data points here. So and then take the average. So this is our regression line. Suppose now we can move this x along the x-axis, we can get a regression line. So this is conditional expectation. So this will be a function of x. But we know that y is again a function of the. I'll write down one more step here. Is g xi, but it's given x, so fixed at x point x. So this x is also a fixed number now, plus epsilon I. Given x equals to x. Because conditional expectation is linear, so we have the conditional expectation of the g x given x equals to x plus expectation of epsilon. Expectation of epsilon, because we assume this is noise. Noise has average 0. So this term becomes 0 now. And also this is not random anymore, because we given x. So this is just the gx. Okay? So if this is the assumption, then the conditional expectation will give us the good function for h that can approximate this g. Okay. So now let's check more detailed example. This is just general idea, but now I will give you two demonstration example. First one is the least square cost function from maximum likelihood. So the question we ask here, we want to demonstrate here is, why do we apply the least square loss function when we apply those regression problem? It says because in the regression problem we assume those error terms, noise follows normal distribution, okay, with average 0. So remember before, the big picture is we assume this epsilon I follows some distribution with average 0 because it represents a noise. So for the regression problem, a lot of cases will assume epsilon I follows normal distribution with variance sigma square. Okay, and this implies our y is follows some normal distribution with some gx xi sigma square. Okay, recall, and based on this assumption, we can find the log likelihood function of the normal distribution. So in other words, log likelihood. Remember the PDF. Density of the yi is given by, so it's just f yi equals to 1 over square root 2 pi sigma square exponential negative 2 sigma square. Okay, yi subtract average. The average is gxi now, minus gxi square. Okay, actually the log PDF y is, so natural log fyi is here equals to so you take a log of this term, so it's just a negative, so natural log cancels exponential, we have the yi, subtract gxi square over 2 sigma square. Okay, and you minus a constant, minus, so you can think it's 2 pi sigma square negative half. You take a log, this becomes negative half 2 pi, right? Log 2 pi minus half log sigma square. Okay, so it's minus half natural log sigma square. The constant we do not care because some constant. Because when we maximize likelihood, the constant does not matter. Okay, and therefore this implies the log likelihood function. So log likelihood function is given by natural log. You multiply all the data points together. Multiply the probability of y1, probability of yn. Okay. And this equals to the log fy1 plus natural log fyn. So each term is equal to this, right? So actually this is equals to negative 2 sigma square summation yi minus gxi square plus some constant. Okay. So therefore, the punchline is here is the punchline here is maximum likelihood on parameter. For example, if you assume this is some function equals to a plus b xi, okay? So maximum likelihood, we have parameter a and b here. Maximum likelihood parameters g, okay, is equivalent to choose g that minimize actually we want to minimize this, right? Minimize this. So we want to minimize this sum squared yi minus g xi. So yi is observed y, gxi is predict I. So this is exactly the mean squared error loss. So this is so in other words, so least square error loss. Okay. So in other words, if we assume some function form g, for example, we assume the linear model, simple linear regression. We treat this g as a distribution parameter. If the noise is not uniformly normally distributed, okay, the maximum likelihood tells us to estimate g is equivalent to estimate the least square error loss. Okay. So that is why when we have these normal errors, we assume the normal errors, we always use the least square error loss. So there are some notes here. If this error follows normal distribution, maybe it's okay. But a lot of real applications, real world problem, the distributions usually a lot of cases not normal. For example, your distribution could be skewed, not symmetric, or it has heavy tail distributions where you can assume t distributions. So if that's the case, if that's the case, maybe least square error loss may not be the perfect case. Okay. So in this short video, I just give you some idea why in the regression problem, lot of regression problem, we use minimize the least square error loss. And in next video, I will tell you more about the logistic regression loss.